Ladies and gentlemen, welcome to the State Key Laboratory of Marine Pollution distinguished lecture. So today we are really glad to have Professor Tan from the University of Hong Kong to be our guest speaker. So it is our great honor to have him. So before we start the presentation, I would like to give you a really brief welcoming remark on behalf of our State Laboratory of Marine Pollution. My name is Kenneth Leung. I'm the director of the State Lab at the same time now as an interim director of the School of Energy and Environment. Dean of the School of SEE. And so our State Lab focus on three research areas. The first one is about marine pollution monitoring and control technologies, especially those innovative technologies. Today's Professor Tan will talk about some membrane technology, which can be applied to remove pollutants, as well as for desalination. So he has been in a frontier in the field. So the second area is about ecological safety and also risk assessment of fuel chemicals and also those algotoxins. The final area is when the pollutants being discharged into the environment, how the marine ecosystem respond to that, and then how can we mitigate and recover the system. So restore the ecosystem. That would be the third area. Then in the third area, now due to the climate change, we also put effort in carbon neutrality. So now the new water treatment technology, wastewater treatment technology, also require energy reduction and promote the sustainability, with harvesting useful materials. So this also under the umbrella of research by Professor Tan. So without further ado, please join me to give him a big round of applause. And now may I invite our organizer, Professor Shen Ziyuan, to give an introduction about our speakers.
Thank Professor Liang. And I'm also a State Key Lab member. I'm Zhi Yuanzhen from Material Science and Engineering in CTU. Today we are very honored to invite Professor Tang to give a distinguished lecture. And before his lecture, let's briefly introduce his background. Professor Tang is a chair professor of environmental engineering at the University of Hong Kong. He obtained his PhD degree from Stanford University and has over 20 years experience in membrane technology, water reuse, and desalination. Professor Tang is a highly cited researcher since 2021. He has published more than 300 journal papers with total citation of 41K and H index of 110 according to Google Scholar, which is really high. And he is also a co-editor of Desalination and a flagship journal on desalination and water reuse. And he has also get accurate inside membrane by Acropole Asia Singapore, which got lots of Professor Tang also gets a lot of awards, including Hong Kong U Outstanding Research Award. Now, without further introduction, now let's welcome Professor Tang for the lecture.
Thank you, Professor Glenn, and thank you, Professor Liang, for the invitation. And I also see many familiar faces, so it's really a good time, my honor to be here to talk about my research in the membrane area. Now, so I will spend most of my time talking about membranes and their applications for water-related application, and then towards the end, if I still have time, then I will briefly touch on the other aspects, energy and something else. Okay, so water, we are lack of water. I mean, even though there's a lot of water around us, but unfortunately, we lack of fresh water supply. If you look at this diagram, look at how many people, actually 4 billion people are somewhat affected by water stress. So in some cases, you can see that the access to water can be rapidly affected by global climate change. So this is the case of Southern California. You can see that within a time frame of 5 years, all of a sudden they say, okay, we have to go for seawater desalination in order to secure enough water. So for this set of slides, I'm going to first of all touch on membranes and their application for water, and then talking about some energy related applications. Now, I started my academic career in Singapore, so I will use Singapore as a case study. Now, Singapore, a very small island, and in this particular case, project, this is called a deep tunnel project. So what they do is that they collect majority of their wastewater, centralize, and trying to treat this wastewater at several centralized wastewater reuse plants. Now, if you look at the statistics about at this moment, about 60% of their wastewater are reused. And going forward, eventually they're targeting to reuse 90% of their municipal wastewater. Okay. And what they do with this wastewater, basically they centralize the wastewater and use technology, which is a pretty mature technology, reverse osmosis. So with reverse osmosis, they turn wastewater into potable drinking water. In Singapore, that's called new water. So if you look at like the plan, in another 30 years also, more than 50% of their water supply will be met by reuse wastewater. Now that's not enough. Still, they don't have enough fresh water. So one step further, they also use seawater desalination. Now, whether you talk about wastewater reuse or seawater desalination, actually the key technology is both reverse osmosis. Of course, I mean, you use different sorts of reverse osmosis membranes, tighter or looser reverse osmosis membranes, but it's the same key technology. Now, in Hong Kong, the TKO desalination plant, this is the first reverse osmosis RO-based desalination plant, which started operation last November, December. So again, this is a reverse osmosis based technology. So if you are interested, I encourage you to take a look. It's a pretty interesting location. So the key technology is membrane. So what is membrane? Now, membrane is a selective barrier. So we are talking about certain selectivity. We want to separate original string into different strings, into different components. So taking water treatment as an example. So you have contaminated, dirty water. So we design membranes to let water passing through our membrane and other contaminants being rejected or retained by the membrane. So there are two very important properties of our membranes. One is permeance. How permeable is this membrane? If my membrane is more permeable, then I can somehow use less membrane area or spend less energy to do the treatment. And another key parameter is selectivity. how selective is my membrane? Can we remove those items we want to remove? So in the membrane fields, there is a well-known correlation or some kind of empirical observation called the upper bound. So basically, we say that if you design a membrane with higher water permeance, a more permeable membrane, they tend to have less selectivity. So this is a trade-off. If you want your membrane to be more selective, then usually you are sacrificing the water productivity, this permeance. So a lot of my research has been kind of centered around how to overcome this kind of upper bound. Can we do something better? So I mean, of course, I mean, a lot of people talk about interesting materials. I'm not really a material engineer or material scientist, but we do read a lot of papers, for example, from Professor Zheng's group, right? A lot of interesting papers. So there are, I mean, to overcome this kind of upper bound. So people use porous materials. It could be COF, MOF, metal organic framework, or zeolites, aligned carbon nanotubes. Now, a couple of years ago, maybe more than 10 years ago, actually, we have been working on interesting material called aquaporin. So this is a natural protein. It is a protein. This is a protein with a defined pore channel. So this the narrowest part is about 3 angstrom. Now, actually, in our human bodies, we have aquaporins. It's very important for our kidney to function, or in our brains, in our eyes. Actually, there's all different sorts of aquaporins. Now, we actually produce aquaporin from E. coli cells. So we basically collaborate with a group from School of Biological Science, and they made some kind of gene editing, and which kind of allow those E. coli cells to overproduce aquaporin. And later, there's a company find a smarter way to do that. They can harvest aquaporin from spinach, so which is much easier. I mean, make it much cheaper. I also know that there is a company set up by a professor at NUS Singapore. They make specifically just produce aquaporins. So our group are very interested in aquaporin, because if you look at the permeability of this entity, so a single protein. So this protein has a size about 4 × 4 nanometer, if you look at it from the top. So each protein contains 1 porin, and each single pore, they can conduct 3 billion water molecules per second. So very fast. If you compare like our best synthetic membrane with aquaporin, so we can easily say this is about 3 to 4 orders of magnitude more permeable compared to synthetic membranes. So we were excited. 10 years ago, we thought, can we do something with this? Can we utilize this entity to make an interesting membrane? Now we actually failed many times. It's almost like one of the most desperate research project I've ever entered into. It's only like so it's a 3-year project. In the last 6 months, we tried almost every single idea. Then we say, okay, maybe we make our life a little bit easier. Initially, we want to kind of align those aquaporin proteins in a planar manner, so that water can kind of directly get through this. But the rejection is very poor, because we can never cover our surface at 100%. If we have 10% defects, that's it. You don't have a good membrane anymore. You don't have the selectivity. So eventually we decided that we assemble these aquaporins into a lipid bilayer. So this entity is a vesicle. So it's basically like a small ball. Inside it's empty. So this kind of vesicle containing aquaporin is called proteinless salt. So we assemble this and then we put this into another synthetic matrix, which itself can permeate water and can reject salt. So here is a kind of simulation within this matrix. So you look at how it's going to behave once you load this kind of protein liposome in the matrix. Because this part, the vesicle is so much more permeable. So it's going to kind of, it's like a highway for water in a way. So it conducts water much faster, but those solutes like sodium chloride cannot pass in this way. So they have to go around it. So in this case, we can, our best recipe, we can triple the water permeance while make the rejection slightly better. So eventually we patented it and we had a startup company. Later it was acquired by Aquaporin Denmark, Aquaporin AS. So now this company is listed in the Denmark tech stock market. So it was a painful journey for me because I mean I have so many nights that I cannot sleep. It was very difficult, and at the end of the day, I mean, even though the performance was good, after optimization, the performance was good, but the cost is also more expensive. So after this experience, we decided to make some kind of a reflection. We basically survey different kind of technology and say, okay, I mean, so if you want to make a technology successful, you need to look at the scale of production. Is this something easily scaled up? You need to look at the cost of fabrication. So is this easy to scale up, or what is the current scale of production, and as well as performance. So I use the size of this symbol to indicate the performance. Now, of course, I mean, things like if you talk about two-dimensional materials, you talk about things like aquaporin, their performance could be potentially very good. But the problem is that in terms of scalability, in terms of cost of production, that can prevent you from the full commercialization. So we were thinking, can we use some kind of conventional materials, conventional processes, but still make our membrane better? So we identified this point. If we use our existing membrane chemistry, so for reverse osmosis or for nanofiltration, typically we use polyamide. But if we design the structure of the polyamide, if we redesign the structure of polyamide, can we make this material perform better? Okay, so if we look back in terms of material development, membrane material development in the context of desalination, so we see one of the very important invention was thin film composite membranes. So basically, thin film composite refers to this kind of structure. You have a very thin rejection film, selective film. So we're talking about this is around a few tens of nanometers to a few hundreds of nanometers. Of course, I mean, this kind of nanofilms is not so stable in terms of mechanical property. So you have to find another support. So beneath it, you have a porous support. So typically, it looks like a ultrafiltration membrane, and of course, you can have another mechanical, another fabric layer to further strengthen up the mechanical strength. So this, and another important in terms of chemistry. I mean, look at this, it's already like almost 50 years ago. But if you look at the chemistry nowadays, we're still more or less using the same kind of chemistry. So for making this selective layer, the best chemistry up to date is this kind of a, we use diamine, we use amine monomer and acid chloride monomer, and they react together to form a so-called polyamide. Forming this polyamide, and so as I mentioned, we up to date are still using this chemistry. But the nice thing about this chemistry is it's pretty straightforward. It's pretty it's cheap. Right? It's cheap. You can produce like a row to row. So our question is, can we make it better using the same chemistry? So now the very first idea, I mark this as 2 because the number 1 idea is new material, right? So, but then the second idea, how to make our membrane better? Can we make our membrane thinner? We produce an ultra thin membrane. Now, one of the ideas we originally developed was to use something like a 3D printing, similar idea. Like if we can kind of use an additive approach, add the material bits by bits. So conventionally, when we make this kind of selective layer, we have one solution, another solution, they react as interface. You cannot control the amount of reactants. So here we decide to use a spray method, electro spray method. One of the monomer, so one monomer, another monomer. We can spray them at a control concentration or control volumetric rate. So in this case, then by controlling the spray time or spray concentration, we can easily determine the amount of reactants enter into this reaction. So for example, here I show you that the thickness of the rejection layer versus the spray time. Now we can control this thickness quite precisely. So it's about like 1 nanometer per minute. So the thinnest rejection layer we made was 4 nanometers in thickness. So it was we thought that it was a pretty interesting idea. Unfortunately, this is another failed attempt. I mean, there was another paper 6 months later. There was a paper published in Science using the same method. They claim that they were successful, but we feel that we were not that successful. Okay, but anyway, more or less the same approach. Now, later we realized, even if you make your membrane ultra thin, there's still some kind of a limitations there. So ideally, if you look at a membrane selective layer like this, I mean, simple resistance kind of a, I mean, if you think about electrical resistance or hydraulic resistance, you know that the resistance is inversely proportional to the length of transport. So if I make this layer very thin, then I hope to get a very high kind of a permeance. Now, somehow, for our membrane design, thin film membrane design, there is another constraint because there is this mechanical support. There is a porous support. So the support there, some parts are impermeable to water, and there's only certain locations you have pores. And typically the surface porosity is on the order of 10% or lower. Now this is problematic for us because if you have water entering at this location, it's okay. They can pass through my film perpendicularly. But what if my water molecules entering at this location? Now they have to travel at much longer kind of a distance. So even if I make my layer very thin, at the end of the day, actually it's this lateral distance starting to dictate the overall resistance. And we can kind of make some kind of a very simple simulation depending on porosity of the substrate. If your substrate is really porous, then there's no problem. There's no restriction from this from the substrate. But if your substrate is very not so porous, typically 10%, then the kind of water permeance you can obtain, it could be 1 order or 2 order below the ideal water permeance. Your selective layer is very permeable. However, because of the geometrical restriction, you are not fully utilizing the power of the selective layer. So we can also see like some, this is a review published by another group. They have, I mean, similarly, they indicate this ideal level, but experimentally, when you make your membrane thinner and thinner, you realize what you can actually get is far below what's available by the film alone. Now, so our next approach, can we make this rejection layer more efficient? Now, as a civil engineer, sometimes we deal with bigger scales, like if you think about irrigation, or even if you think about the design of highway, sometimes you use a so-called gutter layer to conduct water. Okay. So in this case, we can have a similar idea. Now, what if we put in another between our dense layer? This is a layer with high resistance, and this is our substrate. So previously we think that sometimes water has to transport in such a lengthy way, which is not good. Can we put in another layer which is more permeous, so that we let water to pass through this dense layer with very high resistance perpendicularly? So we have we minimize this transport distance. Now, in this porous layer, which is quite water permeable, we let this water to transport laterally. Now, even though the overall transport distance is much longer, but remember, this intermediate layer is much more permeable. So the resistance inside this layer could be more or less negligible. Now, in this case, then you can potentially minimize the overall hydraulic resistance. So in hydraulic engineering, I mean, this kind of a design is very common. But once at a nano scale, I mean, not so many people talk about this kind of phenomenon. So we basically just move like a conventional civil engineering concept to this kind of membrane design. Now we can also do some simulation without the intermediate layer. So the streamline of water transport is like this. So here, you have to go much longer. Not only this is much longer, if you look at the cross-sectional area, towards here, the cross-sectional area is much smaller. But if you use the interlayer, so those water streamlines are almost parallel. So the transport efficiency is maximized. Now, what is the implication? The implication is that if you do a conventional membrane, conventional so-called thin film composite membrane, now, if the membrane thickness is relatively large, it's not a problem. The moment you are trying to design a very permeable membrane by making this selective very thin, you thought this is the ideal permeance. You thought you are going to follow the ideal permeance. But at the end of the day, you are jumping to a region that is controlled by the porosity of the substrate. So your actual efficiency is somewhere here. But if I include this interlayer, depending on the relative permeability of the interlayer, I can boost it up to this level or to this level. And this is a log scale plot. So if you design your system well, this your permeance can be increased by a factor of 100 potentially. Now remember, I started with the story of aquaporing. We said that we tried many things, makes this membrane so expensive, and we increase the permeance by 3 times. But here, the room is 100 times enhancement. And the cost of production is almost the same. So just to show you some example, now, so we use, for example, different layers. Now this is our control without interlayer and with interlayer. Now experimentally, we show a 10 times enhancement in terms of water permeance. And we use another material. Again, the optimized recipe shows nearly 10 times enhancement in terms of water permeance. So it doesn't really matter what material we choose, as long as this intermediate material is permeable enough, we can achieve this kind of so-called gutter layer. It's more like a structural kind of element, more rather than material itself. So with this kind of approach, you can see many of these membranes are exceeding the upper bound. Again, to remind you, this is a log scale plot. So if we are moving towards here, that's a very big difference. Can we make it better? So just now, I introduced a permeable interlayer. Can we make it better? Now, so we started from this control. We put a membrane on a substrate. So with the interlayer, we are kind of trying to avoid this kind of a lengthy transport distance. So with the interlayer, you can align this kind of transport string lines perpendicular to your rejection layer. So if your rejection layer becomes very thin, then this is a very permeable structure. But what if I introduce a nanovoid inside here? If I introduce a nanovoid, so this is empty region. It's an air pocket. Air is very permeable. So this nanovoid can serve as a function of gutter. So this can serve as a function of gutter. But at the same time, by changing this into a three-dimensional structure, from a planar structure to a three-dimensional structure, we can further increase the available surface area. So not only we overcome this problem of like long distance transport, but we also increase the available surface area. So if you think about this, then this one has a dual benefits of increased area plus avoiding this kind of restricted transport. Because of time, I'm not going to get into details of all this, but I would then say, okay, so how can we introduce nanobubbles? How can we design this kind of nanovoids in our rejection layer? Now, so let's come back to this half-century-old chemistry. Early on, I mentioned about this, how do people make this kind of polyamide? They use two monomers, diamine monomer, acid chloride monomer, to form this cross-linked polyamide material. Now, I'm not interested in this chemistry at all. Somehow, one day I was drinking beer. I actually every evening I drink beer. Whatever, mostly IPA, but so I was start to think about this kind of bubbles, nanovoids. And I mean, most of people, when they write this reaction, they stop here because this is the product they want. But actually, this reaction has some byproducts. It's going to produce an acid. And during this process, heat will also be released. So now it's interesting that when I was doing my PhD, actually my group, my advisor do not work on membranes. Is working more on carbonate chemistry. So with this kind of amine solution, we know that amine is the organic base. This is the organic base. So if you measure the pH of this organic base, it's pretty high. You're talking about 9.7, something like that. Now, so if you expose this amine solution to air, what's going to happen? In air, you have CO2. So CO2 will be absorbed into your amine solution. So supposedly, this solution will contain a lot of CO2. Now with CO2, of course, I mean, at high pH, CO2 will mainly exist in the form of bicarbonate. But what happened? Now you are now adding acid into this CO2-rich solution. You are also heating it. So you are acidifying it. It's almost like ocean acidification, right? You are adding acid. At the same time, you are also heating it. Could you, I mean, potentially, can you release those kind of CO2 bubbles again? Initially, you absorb a lot of CO2. Will this process being reversed when you perform this kind of reaction? Now, on top of that, we have another monomer solution. This one usually is dissolved in an organic solvent. Now, the organic solvent, so depending on the kind of a solvent you use, the boiling point of those solvents, sometimes it could be like 80 degrees Celsius, 90 degrees Celsius. Now, there was a paper by Raymond's group at Technion, and they reported that with this kind of heat release at the interface, the temperature, interfacial temperature can be as high as 90 degrees Celsius. So now if you use a volatile organic solvent, could you potentially, I mean, utilize that to, I mean, if you vaporize the organic solvent at the interface, could you take advantage of that to produce nanovoids? So we were thinking along that line. Now, of course, I mean, we want to demonstrate this kind of hypothesis works. So for one example, we want to prove the important role of CO2 in controlling the morphology of membrane surface. Now, remember, we want to produce nanovoids, and we want to show that, demonstrate that CO2 can play a very important role. So our simple hypothesis is that in the amine solution, we have a lot of bicarbonate. During this membrane synthesis, the byproducts, there's acid, there's heating. So that will produce carbonic acid under heating that will release CO2. Now, first of all, let's see. Let's forget about membrane. Let's just simply mix the two solutions together. See whether there will be some gas produced. So we mix these two solutions together. We put a small balloon on top. Okay, now the balloon is inflated. So there are some gases produced. Of course, we can use GC to analyze the composition of the gas. So we show that CO2 is there. CO2 is a major component. Now, but that doesn't really mean that CO2, I mean, we produce CO2, but that does not necessarily mean that CO2 will somehow change the morphology of our rejection layer. So we decide to do another negative control. If we do not remove CO2 from our amine solution, the kind of membrane surface we produce will be a very rough surface. That's because of this kind of morphology. It contains nanovoids. So that makes our surface fairly rough. But what if we remove CO2 before we do the reaction? We produce something with the same recipe. The only difference is that we remove CO2. Now we get a much smoother membrane. So now with this kind of a positive control, negative control, then we can prove that our hypothesis is quite reasonable. And once you understand this kind of mechanism, then you can start to check you can think of many different approach to take advantage of this mechanism. So one very simple approach. Now, since CO2 plays a role, so why don't we just add some precursors of CO2? The cheapest precursor is bicarbonate. Right. So in our membrane making process, we can add some, for example, sodium bicarbonate into this process. We can start to kind of adjust the surface morphology as well as the performance. So indeed, our results show that the resulting membrane become more permeable as well as more selective. And interestingly, I'll just mention this, that it actually also makes our membrane more anti-fouling. Now, fouling is a big issue in membrane process. And 30 years ago, there's many groups. Indeed, in the membrane area, almost everyone is saying that a rougher membrane will make membrane fouling more severe. But we tested. There are some theories. We actually the name of this paper is to pose a question whether surface roughness will increase fouling or decrease fouling. We actually show by understanding the nanoscale membrane transport, we can prove that actually by including this kind of nanovoids, you can make your membrane less fouling. And the reason is that the flux distribution. If you compare the flux distribution of this one and this one, the conventional membrane, it has a very high localized flux right above the membrane pore, but far away from the pore, it has a poor flux. So it's a very non-uniform distribution. By introducing this kind of nanovoids, you can make this distribution much more uniform. And that is, it's good in terms of preventing membrane fouling. Okay, so I need to really rush now. I spent like already 40 minutes. Now let me kind of switch the topic slightly. Now I'm talking about another type of a filter. Sometimes, I mean, not always you want a filter to deal with like a large scale treatment. Sometimes you have some water contamination and you need a very quick fix. Think about like in emergency cases, after a tsunami, after earthquake, you may not have water, but you may not have electricity supply. So can we get some kind of a filter which can provide some kind of a rapid fix to do detoxification of water? So here we design like this kind of so-called nanofiber membrane. It's a very common technique. We use again with electro spinning process, makes this kind of fibers. These fibers are stacked together and we functionalize the fiber. Then we can use this fiber. This kind of pore size is small enough to remove microorganism bacteria. At the same time, you can rely on absorption to remove things like lead, this type of contaminants. So if you make the this kind of fiber permeable enough, so in this case, you can see this height is roughly about 5 centimeters. With 5 centimeters of water head, by gravitational force, water will drip down by itself. So very permeable. Now, of course, I mean, this is still too slow. This is still too slow. So we decided to make like a little trick. I mean, we say, okay, at the end of the day, we want something you can easily carry around. So we purchase this kind of foldable cup. We put the 2 cups together in between. So in between is our filter. So you can stretch it. You can put it in your pocket. But the magic thing is that I mean, initially, so the dirty water is put on top, and the bottom one you can stretch it. By stretching that, you create a vacuum. And with this vacuum, you can accelerate this water permeation by more than 10 times. So in 30 seconds, within 30 seconds, you can fill up this cup. Right. So we thought it's like an interesting attempt. So this is a kind of concept. Of course, I mean, you can make it bigger. So this is a cup. You see, you can fold it. You can put it in the pocket, carry it around. Of course, I mean, this kind of materials can also be used for air filtration, other purposes. Now, not only, I mean, membranes, not only we're talking about making it very permeable. In many cases, you need to think about what kind of contaminants you want to remove. For example, I know nowadays in environmental area, everyone is talking about perfluorinated compounds. I did research on like probably I produced the first paper on like using nanofiltration membranes for PFOS removal. That was like during my PhD days, and one day we were approached by a semiconductor industry. They say that they have a wastewater containing 1.6 gram per liter of PFOS. 1.6. I mean, normally you are talking about ppb. ppb is already very high, ppt. But we were talking about 1.6. You know, the solubility of PFOS in water is 0.5 gram per liter. So the amount of PFOS is more than the solubility. Of course, I mean, in semiconductor industry, you also have alcohol, like isopropyl alcohol to increase the solubility. But anyway, so I'll say, I mean, there's whole lots of contaminants. In desalination, usually we talk about sodium chloride. But in many other cases, sodium chloride it's nothing. I mean, who cares about sodium chloride? You should care about whole lots of other far more toxic compounds. So unfortunately, at this moment, most of the membrane literature, they are talking about, when you talk about whether a membrane is good or not, people are usually talking about the rejection of mineral salts versus permeants, because of their origin of, I mean, most of this kind of nanofiltration, reverse osmosis, they originated from the desalination field. So my argument is that in the future, you need to think about this kind of contaminants, especially you probably want to design your membrane in first principle against this. How can I design a membrane to better remove this? Due to time limitations, so I mean, we do have some kind of research projects on this aspect, but due to time limitation, I'll skip this. But if you are interested, we have published a review paper in ESNT letters, so you might want to take a look. Now maybe the final 10 minutes or so, I'll say now membranes can be used in many other applications. You can use it for resource recovery. You can use for energy production. Now, this work was done like 10 years ago. We are trying to use a high retention membrane in a bioreactor. So talking about membrane bioreactor, I mean, membrane bioreactor is one of the probably most successful technology in the environmental domain in the last 20 years or so, last 30 years or so. I mean, it has been so widely applied in wastewater treatment. But most of the membrane bioreactors, people are using porous membranes, microfiltration or ultrafiltration. So my argument is that by using a dense membrane, a high retention membrane, you can probably get a lot of whole range of new opportunities. 10 years ago, we were working on a process called forward osmosis. So that time we are trying to use forward osmosis process to pre-concentrate our wastewater. Now, once you pre-concentrate, let's say municipal wastewater, then you can, now you get concentrated wastewater, which is high in COD, high in BOD. Now you can do anaerobic treatment. You can convert the bioenergy into hydrogen or into methane. You can recover nutrient. But unfortunately, forward osmosis is pretty expensive in terms of process run. So now my lab is now turning to use very highly permeable nanofiltration membranes. We have recently developed some kind of nanofiltration membranes with 0.1 bar. We can drive a high enough water permeance. Now think about even for ultrafiltration membranes. To operate an ultrafiltration membrane, you probably also need this kind of a vacuum difference. So now we can make a membrane, nanofiltration membrane, as permeable as nanofiltration. So we are moving into this direction, trying to apply it for in wastewater in membrane bioreactor. Now, one step further, indeed, why don't we use this for water reuse then? If my membrane can already reject toxic compounds, can reject those microorganisms, then I can use it for water reuse purpose. Maybe I don't have the time. So anyway, membranes can be used for energy production. In this case, it's a salinity gradient power. It's basically like chemical potential energy. So between ocean and the river, there's this kind of chemical potential energy. Now, I'll just very quickly introduce this work. This is a collaboration with HKUST. Professor Cecilia, he has already left Hong Kong, but he was an expert in developing this kind of inorganic membrane with single ion conductance. So this material is only conductive to sodium, not any other ions. So that means the selectivity of this material is nearly 100%. So we utilize this kind of material with a high sodium concentration on one side, lower sodium concentration on the other side. Then we can establish under this concentration gradient, we can establish ionic flux. And this ionic flux can be converted into electricity. So now we have also did some kind of very minor work. I mean, this far from application yet. It's only some idea. Now, sometimes, I mean, if you're trying to relying on inorganic, the concentration gradient of inorganic salts, now how many log scale can you have? I mean, in terms of a concentration difference, how many log scales can you have? Maybe like 2 logs, that's 100 times difference. Because the chemical potential energy is proportional to the log of C1 over C2. So if the log scale difference is only 2 log difference, then the amount of energy is limited. But what if you have like other type of chemical potential energy? For example, if you have a acid base. So if you have pH 1 versus pH 13, that's a 12 log scale difference. Then now the amount of energy available to you is so much enriched. So here we take we analyze, for example, here, if you think about acid mine drainage is a naturally kind of available kind of waste with very low pH around pH 2. And typically people, I mean, this is a pollution source. So people need to kind of treat it. So usually you use lime to neutralize this. So, but there is a chemical potential gradient. So if we realize this kind of chemical energy available, then indeed we can set up something like a nature-powered battery. With one side is the waste, the acid mine drainage, and the other one is the lime source. So you can do this neutralization in a controlled manner. But I mean, as I mentioned, this is far away from real applications. The amount of energy, I mean, you can, the energy density is pretty high, but the total amount of energy, because the typical AMD site is quite limited. So it's you're talking about a few hundreds to a few thousand kilowatt hour kind of daily production. So anyway, I should probably finish my my talk here. I'll just say, I mean, in future, materials are still very interesting. But my argument is that material plus a better understanding of the transport. If you can also make this kind of a structure better to facilitate, to best utilize the power of materials, then this could be very exciting. So our group are kind of trying to collaborate with different groups to realize this kind of opportunities. We have also been establishing an open membrane database, so collect all the reported literature, putting it to a platform so everyone can access. So we can see like over years how membrane performance has been kind of been improving or what's available. And I'll say now membrane material itself is not enough. You have to understand the process side. Now, although I don't have time to touch on the process side, but I'll say the same membrane for different processes. Sometimes if you make you thought that you made a better membrane, sometimes it can be a disaster. If we put a very highly permeable membrane into desalination without a good process design, maybe within a week, that membrane will be easily fouled and the plant may have to be closed. So everything has to be side by side. Material, synthesis, membrane synthesis, and process design. So we're also trying to look into other opportunities, for example, making membranes to deal with more extreme operational conditions. So with this, I should really stop. This is like a kind of this is our lab. So everything is about membrane, how to make membranes. Hey, thank you so much.
Thank you very much for your for this very exciting talk about membrane technology, not only in scientific research but also in real product. It's really knowledgeable. Now, questions from the audience.
And then I can answer first. Thanks, Professor Kang. It's a very fascinating talk. So I actually have two questions, one about small, one about large. So the first one is about your interlayer story. That's very fascinating. But here I was thinking because we talk about it's just about the surface porosity. So that's does that also mean that if we directly make one integrated structure, asymmetric support that's going up, or if the robustness of the interface is going up, we can directly use that as a support? Or the addition of the interlayer has some other effects?
Okay, well, I mean, that's a very interesting question. Let me see if I have, so, I mean, we started, I mean, if you look at back to the history, we started with this kind of asymmetrical structure. This is another material, cellulose acetate. So, I mean, the very initial attempt is like a more uniform membrane structure, and then people realize by accident that if you make this structure asymmetrical, its permeance will be greatly enhanced. With this structure, the typical skin layer thickness is about 2 micrometers, 3 micrometers. Why this represents a major leap against this? Simply because this is much more thinner. This layer is much thinner. Now, once I presented a proposal, say, can we make an asymmetrical, I mean, programmed asymmetricity in this layer? If within this 100 nanometers, you can also make this layer kind of asymmetrical, then potentially you can solve that problem. So for example, with this kind of a spray method, if you make a less cross-linking linked recipe first, and then you're trying to spray a more cross-linked recipe at a later stage, then potentially you can make a good design. Now, in most of the cases, but still, I mean, that process is less scalable. In most of the, I mean, with the current way of making membranes, we basically have one solution here and another solution in the organic phase, they meet together, you have very little control. You have very little control. So how do you control the asymmetricity? I'm not so sure. I mean, maybe someone can do it. So I don't know whether I answer your question.
Yeah, thank you. Another question is about actually your first story about the aquapooring. You showed the potentials of I mean scaling up and also different costs. Because I've been talking with my students in the class about this. How do we have considerations on new technologies, new materials? I want to hear more of your thoughts or comments on considering about the potential of scaling up of new material or new technologies, because we may not always use a new material for desalination or large scale water treatment, but for example, in your kitchen, in your household, something like that. So I was just wondering, want to hear more of your comments on thinking about the scalability of the area.
Yeah. Now, even with the same materials, the scalability, depending on your membrane structure design, the scalability can be very different. So again, let me get back to aquapooring. So the one we produced eventually was this form. This is, I mean, since you are in the membrane area, so you know TFM, thin film nanocomposite membrane. I mean, essentially, this is a composite structure. We are only kind of using this as a permeability enhancer. We are trying to create this kind of so-called preferential water transport channels. But still, in this design, we need to use this matrix. And this particular matrix is polyamide, the same material. Now, because of the use of polyamide, then this technology is reasonably scalable. We can still use the same kind of existing production line, except that we need to produce this additional protein vesicles. So in that case, I mean, if you check the company Aquapooring Asia or Aquapooring AS, they're already making like membranes of thousands of meters squares. It's possible. In terms of cost, it's about 30% more expensive than conventional approach. So 30% more, 3 times more permeable. Do you have the market in desalination? Actually, unfortunately, they're still struggling to sell their membranes. But in household applications, they have been quite successful, or for industrial wastewater treatment, there is a market for them. Now, the same material, you have another way to process this material. You can try to align this aquapoorings in a planar manner. So what is the difference? In this case, this is a lipid bilayer, which is impermeable to water and impermeable to solids. So all the water or any solids passing through the membrane, they have to go through this aquapooring, which means that the selectivity of the membrane is directly dictated by aquapooring itself. Or if you make a very good membrane without defects, then selectivity is almost perfect. Aquapooring doesn't even allow proton to pass through this channel. So perfect selectivity. But how big can we make? I mean, there are like about 20 to 30 papers on making this kind of membrane. How big can you make? You're talking about millimeters by millimeters. So do you expect this to be used for water filtration? I mean, you can use this to write a fantastic paper, but probably not for any real application. So again, I mean, it's kind of a trade-off. Where do you position? We originally were kind of planning for this, but eventually we have to give up and get back to here.
Thank you, Professor Tom, for your impressive talk. And because you mentioned aquapooring, I think that this is the channel only for water transport. And it reminds me of the potassium channel.
Ion channel.
Potassium channel, which only allows the passage of potassium. So my question is, do you have any perspectives for the membrane? Because, you know, the selective ion sieving will be, I mean, will be promising in the future,
Mhm.
like in the area of the lithium extraction or the uranium extraction or some other cations. So my question is, do you have any perspectives for or comments for the membrane and which way can we go further in the membrane design, like in the TFC polyamide membranes or some other materials?
I mean, this is something I look forward to learn more from you. I mean, aquaporin and this kind of ion selective channels, ion selective porings, they were awarded Nobel Prize in the same year, right?
Yeah.
So it's 1994, I guess. But apparently in the membrane-related field, there's a lot of people working on aquaporins. For the ion selective channels, it seems that in the domain of sensors, there's a lot of people kind of getting quite interested. We are interested in ion channels as well, but at the moment we don't have a good idea how to utilize it for what purpose yet. But I mean, of course, I mean, a lot of interesting work comes from cross-talking and collaborations. So hope that we can talk about this more. Now, indeed, I mean, not only this kind of natural porins, there's, do I have something here? No, there are this type of synthetic channels. I mean, whether it's synthetic water channels or synthetic ion channels. The argument is that with this kind of natural protein, for one thing, you have like 4 by 4 nanometers, but your channel is only 3 angstrom. So you are not effectively utilize the area. You only utilize about like 2-3% of the area. So if one can make this kind of synthetic channels, then the packing density can be much higher. So we have been collaborating with a group in France. They are making this kind of artificial water channel protein, artificial water channels. But again, it's not as easy. I mean, we do have some results, some positive results, but it's not easy.
And Professor, another question is, considering the background, you know, the nuclear wastewater from Japan, do we have any measurement in Hong Kong to prevent or to purify the water?
Okay.
The seawater, we have the nuclear, you know, the uranium, some other element.
Okay, I mean, if you talk about using membranes for urine to stop uranium, that's very easy. Uranium is so bulky, so that's not problem at all. But if you talk about those isotopes for hydrogen, then I mean, it's very tricky. Yeah.
Thank you.
Any questions?
Thank you, Trian, for a very inspiring talk. It's really fascinating to see civil engineering knowledge and skills influence the design and the manufacture of nanoscale materials. I actually have a very general question about membrane fouling. Some 10 years ago, 10, 15 years ago, it was such a hot topic. And an editor of a journal, we received a lot of papers on membrane fouling. Now, seems that topic is getting much colder, like. So I'm just wondering, as a non-specialist of membrane, I'm just wondering if that is issue largely resolved, like new membrane materials are less prone to fouling, or people just accept it? That's an issue you have to deal with.
Yeah, that's a very good question. I inclined to say this problem is not fully resolved. I mean, there are people making better materials to improve antibacterial and anti-adhesion properties. But at the end of the day, depending on how you use membrane, the way you use the membrane is probably more important than the membrane itself. So, I mean, at the end of the day, people say, okay, we'll have to, in the water treatment domain, for example, if you run a membrane bioreactor, then sooner or later you have to clean it. You have to, so you have to solve it, solve this problem through operation maintenance kind of design. I guess, I mean, in terms of membrane fouling, I mean, the peak was like in the 90s and early 2000, a lot of people working on membranes. And at that time, especially in the 90s, there's not a very good theoretical framework in terms of membrane fouling. But then after that, after people talk about the critical flux concept, so basically they say, okay, I mean, at the end of the day, as long as you operate your membrane carefully below certain threshold flux value, then you can operate for a longer time. So so I mean, after this kind of a concept being more widely accepted, then in terms of theoretical breakthrough, there's less opportunities. I mean, that's my personal view. There's still a lot of operational observations. But then the problem is that if you observe this in this treatment plant, you change to another plant, it may not be like so easily transferable. So like when we start to read, actually my PhD topic was membrane fouling. So that was like 2002 to 2006. At that time, I still see like some interesting problems to be discussed. But then later, for a while, I feel there's less opportunity to think in terms of theory. But lately, I also, again, I see, okay, maybe there's a lot of things still not fully understood. Even like the very simple discussion, like how does roughness affect membrane fouling? 30 years ago, I believe in other groups that rougher membrane fouls more easily. But now we tested many of our own membranes. We have this, we consistently observe that if we use similar recipe by making a smoother membrane versus a rougher membrane, with many different kind of foulants, we consistently observe that the rougher membranes fouls less. So it's like almost the entire field believe in this direction. Then you all of a sudden feel like, okay, actually, it may not be true. So there's still opportunities. Yeah, thank you.
Yes, Professor Tam, thank you for such an inspiring and really interesting talk. I think all of us learned a lot today, and we really appreciate the way you try to think some ways to improve the technology. So I remember you say that when you was young, you also try to use the membrane to remove PFAS, the performing-related carbons. Since many of us working on PFAS here, we try to develop passive sampler for PFAS since they are in a very low concentration. At the same time, we also want to remove them from the wastewater. So since now you have more knowledge on the membrane, if we ask you how to make a better membrane to tackle these pollutants, how you going to design your new membrane?
Okay, so talking about, I suppose there are many strategies. I mean, from the membrane domain, there's different strategies to think about like how to tackle PFAS. I mean, in terms of enrichment. Of course, I mean, there are catalytic membranes, potentially you can design it to destroy PFAS. But if you just talk about physical concentrating, now, one way is you design membranes that allow water to flow through, and PFAS is relatively big. I mean, the molecular weight is 500, I guess, or maybe 499 delta. So it's big enough, and it's a pretty rigid molecule. So indeed, to separate PFAS from water is relatively easy. Even if you buy a commercial membrane, you can easily get more than 90% rejection by nanofiltration membrane, or if you use an RO membrane, 99% rejection. Of course, I mean, sometimes if you want this membrane to be more permeable, then our knowledge domain will start to kick in. Right, so we can maintain very high removal while still you could potentially use a vacuum instead of using like a high pressure. Typically, for
That sounds like really good collaboration opportunity. Yeah,
that,
let's work together.
that's great. That's great.
Thank you.
Yeah, so we do have membranes that you can use a suction just to concentrate your samples. Yeah.
Okay, any more questions?
Thank you, Professor Tang, for your very interesting talk. So I'm not working on membrane, but I'm working on some electrocatalysis, which use membrane frequently. So I have a question regarding, so I wonder whether do you have any thought or comment about the membrane, whether if we have some alcohol and water together, and we want to separate water and alcohol, so whether there is some good membrane can do this kind of thing, because as I know, such as the naphthalene, that kind of membrane, so when they using the methanol and the water together, so they always will say some methanol and the water will transfer to another size together. So then I wonder whether there is some good development and design in this.
Okay, so it's a very good question. Probably you may not want to use the kind of membrane I introduced here. You might want to use some other membrane processes such as permeability. So I mean, here, the kind of membrane I have introduced is more like a pressure-driven membrane. You push these solvents, solids through the membrane. But permeability, you're also relying on the different kind of volatility. So the more volatile components versus less volatile components. So there are this kind of membranes available. Yeah, so potentially you can consider that.
Okay, any more questions?
Just check whether.
Yeah, any more questions from the online? Okay, I just have one quick question. So you mentioned that roughness can influence the anti-fouling property. I'm just wondering if, let's say, a small feature create small feature to increase roughness, and also functionalize some, let's say, hydrophobic or hydrophilic functional group is kind of useful or not?
Okay, now when I say roughness help, I actually come from certain assumptions. And the assumption is that that roughness was created due to the nanovoid. Now, to make it more general, whether a rougher membrane make fouling worse, or whether kind of reduce fouling or increase fouling, actually, I don't have an answer for you, because I don't even, in our literature, we don't even have a very good definition of roughness. Now, how do you define roughness? You could have this kind of triangles versus a triangle like this. So if you, at this moment, if you report roughness, whether it's average roughness or kind of maximum roughness or RMS roughness, mean square roughness, they all have the same value. The two patterns share the same value. But do you believe that this pattern versus that pattern has the same fouling tendency? Depending on which angle you trying to look into this problem. For example, in terms of hydrodynamics, if you have a so-called cross flow velocity, cross flow over the membrane surface. So the membrane is like a piece of paper, right? You have another flow on top to trying to create some shear. So depend on the aspect ratio of this, the local mixing will be very different. So in certain cases, if this value is very sharp, then my intuition tells me that the fouling will be more severe because you create a lot of that value. But if you have like a gentle slope with this kind of a protuberance, you can actually promote. In certain fields, this kind of features are used to promote mixing, promote local turbulence. So, without defining the roughness clearly, it's very difficult to conclude which one is better. Now, of course, your question is more from material side.
Yeah.
And that one, I still need to learn a bit more, and then we can discuss a bit more. Anyway, my little conclusion is only based on that if we have this nanovoid, then this the resulting roughness will be good for us.
Okay. Any more questions? Or if no more questions, then.
As you just say, the nanovoids maybe make the pores of the membrane make a larger permeance. But if you are in reverse osmosis, it's always have a 10 bar or 100 bar. That high air pressure maybe make your nanovoids become from the rough to the light.
That's a very interesting question. Now, actually, for my bachelor degree, I was a structural engineer. So, and for my master degree, I investigate on a type of structure called deep beams. So again, it's a structural element. Deep beam is a type of beam. So you know beam, right? Beam. So this for normally the beam is like a typical beam is this span over the depth is more than 3 or more than 4. That's a normal beam. For deep beam, it's like the depth of this is almost close to the span. So the force transfer is very different. Typically, a typical beam is by bending moment. But in a deep beam, the force transfer is by this kind of diagonal compression force. Now, why I mention this? If you think about some of the old bridges, like arch bridge, so you observe the depth, the span. It's all 赵州桥, right? Their force transfer is different from this kind of bending moment. It's by compression. And the material could be very weak in tension or in bending, but they can be very strong in compression. Now, think about what kind of a structure we have. We have a dome. If you look at the 2D structure, it's more like an arch. So the force transfer is mostly by compression. And do we have experimental result to show that? Actually, we tested our membrane 30 bar, and we look at on the SEM or TEM, we look at the structure again. We do not see the kind of collapse of those nanobubbles. Okay. However, You also made a very good point. Are those structures stable or not? I don't know whether I have results. They may not be always that stable. They may not be always that stable. If we make a membrane and we dry it. Now this is a AFM measurement. So we made a membrane. We made a membrane which is in a wet state. So look at this kind of a structure. It's a rounded structure. It's those kind of so-called bubbles. These are air bubble and enclosed by our selective layer. So you have produced an air bubble, but capsulated by the polyamide material. So they are rounded. Now, if you start to dry them in air, what's going to happen? So this one with time, because of the capillary force, when you dry it, it may collapse. Now, if you start to test the performance of this membrane, original membrane versus this one, the structure is collapsed. Now, the rejection is still well maintained. So the selectivity of this membrane is still good. But in terms of permeance, it will be much reduced. Okay. So if you talk to some of the membrane manufacturers, they will tell you never dry my membrane. Once my membrane is dried, the performance will be different. When I was a PhD student, I didn't understand why. But now when I look through these kind of details, now I know, okay, I mean, the nanoscale structure are changed. They're able to withstand this kind of high pressure. We have good evidence that these are not a big problem. But actually, this kind of drying is worse. Now, actually, in membrane manufacturing, there is also a post-heat treatment, typically like the temperature raised above 60. So this step is very tricky. You have to do something to maintain the structure. So, for example, you can use glycerol. You coat this membrane with glycerol, trying to maintain the structure of this. Otherwise, if the structure collapses, then the membrane performance is totally different.
It's time for IPA. Oh, yeah, yeah. So if we have more further questions, you can directly contact Professor Tang. And let's thank Professor Tang again.
Thank you.